This is example problem 1 for the big 5 acceleration equations. We start off by reading the problem. A car begins to roll down a hill, accelerating at 1.8 meters per second squared. How fast is it going at the end of 4.2 seconds? So we begin by drawing a simple little sketch. This is the hill where the initial velocity was. Here is my car. It's a box, but it doesn't really matter what the car actually looks like. We're just pointing out that it is accelerating down the hill with a particular amount of displacement. I next need to list out my information. So I have my initial velocity, final velocity, acceleration, displacement, and time. The initial velocity, it's not actually given numerically, but it says it begins to roll down a hill. So that would imply I'm starting from rest, 0 meters per second. The final velocity is what I'm looking for. The acceleration is given as 1.8 meters per second squared. The displacement I'm not really interested in right now. As I can see, I'll need to solve for that later on. The time is 4.2 seconds. So now I need to figure out what equation I'm going to be using here. If I don't care about displacement, then it looks like it's a VVET problem. VF equals VI plus AT. Nice thing about this is it's already solved for me in terms of getting VF all by itself. And as I can see, the initial velocity is 0. So I'm just going to cancel that out. VF equals AT. And now I can start plugging in. And I have 1.8 meters per second squared. That is multiplied by the time, which is 4.2 seconds. And I tap that into my calculator. Tap, tap. 7.56 meters per second. Of course, with significant digits, that should be about 7.6 meters per second. And I can double check this. I've been going along with my units. They are working themselves out. And I can say if the acceleration is about 2 meters per second squared and the time is about 4 seconds, 2 times 4 is approximately, well, is 8, but that is pretty much the same thing as 7.6. So that makes that pretty good. Now I can move on to the second part of the equation, which is, or the second part of the problem, how far has the car traveled during that time? Okay, so I'm now looking for the displacement. I'm going to keep the same drawing and I'm going to keep the same list of information, but as we can see, I'm looking for how far, so that means this is going to be my question mark. And even though I have actually solved for my final velocity, which is the 7.6 meters per second, I'm going to pretend I don't know that because just in case I made a mistake over here, I don't want that to mess up my information. So I'm going to ignore I'm going to use the equation without v final. I'm ignoring what I just solved for. And I have the 1/2 AT squared equation. D equals VI t plus 1/2 AT squared. Once again, I know initial velocity is 0, so this whole thing will cancel out. That's very nice. Okay, I'm looking for displacement, so that means it's already rearranged. So that's great too. So D equals 1/2 AT squared. Then I can just plug in 1/2 times the acceleration, which was 1.8 meters per second squared, then times the time, which was 4.2 seconds, and that whole thing is squared. So now I tap into my calculator. Displacement equals 15.876 meters, and then putting in with significant digits, displacement is 16 meters. And the units once again cancel out because this seconds end up being squared from out here, so that canceled out with those seconds. And then I can just look through with my numbers. The 1/2 times 1.8, 1.8 once again is about 2. So 1/2 times 2 is 1. And then times 4 squared is going to be 16, which actually is the answer. So hooray, the checking worked out perfectly.